Hey, everybody. Thanks for coming out. My name's Chris, and I'm here to talk to you about Geo. It's a cross-platform GUI toolkit in Go. I do not know how many of you may have caught my talk this morning. If you were not there, raise your hand, because I want to make sure that I cover. Yeah, okay, good. So my goal for this hour-and-a-half period we have is to try to equip you with understanding what this thing is, and also to get your hands dirty if you've brought a device capable of doing development. But in order to do that, you might have to install a few things. I don't know if you already have, say, Go installed on your computer, but we will need that. So the high-level description of what GUI does is we provide a common API surface that lets you build a GUI application that will run consistently on Linux and macOS and Windows and some of the BSDs and Android and iOS and in the browser, and even some more obscure targets than that. And the way that we do this is by providing several different layers of API that you could choose to consume. And we're going to look at kind of two of those different layers today. At its lowest level, you can think about GUI as a sort of virtual machine with instructions that allow you to build a description of a frame of a GUI. And then you build an event loop where you create a description of a frame of GUI that you want to show, and then you ask GUI to show it, and you repeat this as necessary. But that's fairly low level. That's the sort of API that you would use if you were trying to implement your own layout system, your own widget system, your own everything. And you're welcome to do that on GUI. We provide this low-level API so that you have that option. But we also provide some higher-level abstractions. We provide a layout system that is inspired by one in Flutter, though not identical to it. We provide a set of widget state types that encapsulate, what's necessary to make a button, what's necessary to make a text editor, simple one. And we also provide an implementation of material design aesthetics for those widgets. But if you don't like material design and you want to use something different, you can build your own theme and reuse the state types that we provide, or you can rebuild the state types, or you can rebuild your own layout system. You choose the level at which you want to work with it. So for starters, what I'd like to do, I have this repo on SourceHut that if you'd like to play along, you can clone. And I'm going to take us through the sort of low-level API. In my talk this morning, if you were there, we talked in just English with no code about how to build a very simple animated button. And so the first thing I'd like to do is show you what that looks like in actual code. How many of you have never seen or written any Go? Okay. Have you written C? It's okay if the answer is no. Okay. So the syntax may be somewhat unfamiliar, but we'll do our best. So GUI does have some dependencies. On Linux, they're probably mostly already available, but there's if you can find my repo. I'm sorry that my username is so long so that you have to type so much. I link to the platform dependencies that we have, and you can choose your particular platform. On Linux, you need Go. You need the development headers for system graphics libraries, because GUI uses your GPU to do everything. And you need, a handful of other development header files. On Mac OS, you just need like a C compiler toolchain. Clang, the one that ships with Xcode, is fine. On Windows, you usually just need Go. But for today, one of my demos does use SQLite. And so if you're on Windows, you'll also need a C toolchain because SQLite is in C. All right. So I've tried to document the requirements here, and you can test whether or not you have a working environment after you've cloned the repo by trying to run this command. But I'm going to kind of dive in to what our low-level API actually looks like. So this file that I have open, ops only button, is an implementation of an animated button using only raw GUI operations, so the lowest level abstraction that we provide. So what I'm going to do is I'm going to make an application window, and then I'm going to draw a button inside of it with an event loop. So in Go, our entry point is the main function. And in order to function correctly cross-platform, we have to structure it in a slightly strange way. Some platforms, cough Mac OS, require special things to happen on one of the threads. And so we have to essentially sacrifice the main thread on that altar and say, okay, when we start the app, here is the main thread. It has to do the special things. So we're going to launch a new Go routine to run our application logic. And the main thread will do what it needs to do on the platforms that it needs to do that on. And on the other ones, it'll do nothing, but it's not really expensive. We're going to make a new window and configure it. We're going to set a window title and some size constraints. And we pass that new window immediately into an event loop function. So if you jump to its definition, I think it's the last function in the file. If you've seen an event loop before, this is going to be kind of familiar. We're going to initialize a handful of things that we need in order for our application to do anything, some state tracking. And then we're going to run a loop over events coming to us from the window. So a GUI window produces certain events. The most notable are the destroy event, which is what happens when either the user or the operating system is tearing down your window. The other one is a frame event. A frame event says, hey, you need to draw a frame. And that's what we're going to spend most of our time doing, is drawing frames. And essentially, your application runs this event loop until the window closes, and then it's gone. And so in our event loop, we declare a handful of things. We're going to need a text shaper because we're going to display some text, and we can talk a little bit later about what that shaper actually does. We're going to display a button, and so we're going to need some state to track that button. We're going to need an operation list. So GUI defines a frame in terms of an operation list. We build an operation list, and then we give it to GUI to display. And this separation is interesting because it lets us describe the visuals of what we want to show without doing any of the work of showing them yet. And then when we give that operation list to GUI, it has the opportunity to compare the operations against the ones from last frame and skip redundant work. And also, we can express what we want to draw in very compact data. You can think about GUI's rendering model as similar to like vector image formats in that we kind of describe the spaces that we want to manipulate and the colors or textures that we want to put into them. But that's actually not very much data, right? You describe the outline of something and then what you want to fill it with. That's way cheaper than a buffer of pixels that are all that color and that size. So to render a frame, we take the ops list that we declare up here, and we're going to insert a bunch of stuff in it. The first thing that we're actually going to do is fill our window with a color. So there's two GUI operations for this. Paint.colorOp, which we're using here, is what sets the paint material to a fixed color. You can think about this like if you're using a drawing application, there's always a way to choose what color you will draw in the next time you use, say, the paintbrush or the pencil tool, right? So this is sort of the picker for what color or other material you're going to work with when you next do a paint. But this doesn't actually change anything visibly. And then we issue a paint op. And the paint op says, hey, take whatever the current area that we're working with is, and that's implicitly the entire window when you haven't narrowed it, and fill it with the current paint material. The paint material can also be things like a gradient or an image, but in this case, it is just a color. Here, we are going to update the state of our button. So basically the button gets to consume click events and touch events and decide whether or not it has been clicked. And we'll look in detail about how that works. And then we ask the button, hey, draw yourself. So to draw itself, the button inserts a bunch of operations into this same operation list that we used earlier. And after it has done that, we say, hey, GUI, here's a complete operation list. Please display it. And this particular example program has a facility where it can actually dump PNG screenshots of every frame. And I used that in order to make my my other presentation. That's not active by default, but that's what's happening here is it's rendering a second time to a headless off-screen window to generate PNGs. And then the operation list, we truncate it, we empty it. And that allows us to reuse the memory that backs it for the next frame. So we buffer up a whole bunch of operations, we hand them off to GUI, which is going to do the render and the input configuration and all of that. And then we empty the operation list in preparation for the next frame. And this is the cycle that we live inside. So now we can look in some detail at the implementation of the button. So button has an update function. And this update function is where we're going to check whether the button has been interacted with. So the low-level API for this is that when we get a frame event from GUI, it has a field called queue. And the queue supplies events that have occurred since the previous frame. And so we ask the queue, hey, do you have any events for this tag? A tag is an arbitrary value that each widget just needs to choose, and it needs to be unique for that widget. So usually what we do is we use the address of the stateful part of a widget because it's guaranteed unique within the scope of the application. So this button is asking, hey, are there any events that have been routed to me? And we get multiple of those back. We get a slice. And so this for loop is actually iterating over those slices and saying, hey, what is their concrete type? Because they come back to us as an interface type. They could be many concrete things. So we check, is it a pointer event? Because if it's not a pointer event, we don't actually care. So if it's not a pointer event, we're going to skip it. If it is a pointer event, we want to know what kind of pointer event is it? Is it GUI letting us know that the current gesture is canceled, which is a thing that happens when GUI doesn't yet know what a gesture is. Like there's a disambiguation phase that has to happen when you start touchscreen multi-touch gestures and stuff, where the input routing knows that a touch is occurring, but it's not sure yet whether it's a pinch or a scroll or any number of other things. So cancel lets you know, hey, whatever you were doing, stop. In our case, we're working with a very simple gesture, so it doesn't matter. Clicking is easy. So if we detect a press, if we detect that either the mouse has been depressed or like a finger has depressed on a touchscreen, then we want to say, hey, a press has started on this button. And if we detect a release and we also had a press in the past, then we're going to note that we're no longer pressed, and we're going to record where that press event occurred within our button and when it occurred. And then we'll record, hey, actually a click did happen, and we'll let higher level application logic know that a click happened because frequently it wants to do something, you know, like buttons usually do something when you click them. And that's what that's doing. So this is the kind of simple state update function for our button. The other thing our button does is draw, right? It needs to display itself. And this whole function is just going to be inserting a bunch of GUI operations into the operation list to describe the button. So the first thing that we want to do is make a nice rounded rectangle that is our button. I suppose this would be a good time for me to show you the button in case you haven't been able to run it yourself. Oh, look, beautiful, a button. And it's animated. Magic. So this is what we're doing. This is the code that we're looking at, is how to generate this thing. And I apologize for the absurd size of my window decorations. Making things visible is required scaling up quite a bit. So the first thing we want to do is capture the rounded rectangle that is the outside of our button. And the way that we do this is using the clip package. So GUI provides a number of operations in different packages, and they're sort of scoped to different kinds of information about your UI. So the clip package is all about selecting parts of the logical space on the screen so that you can manipulate them with other operations. And we want a rounded rectangle, and we specifically want a uniform rounded rectangle, which lets us supply the corner radius only one time instead of 4 different radii for 4 different rounded rectangles. So I specify there is a rectangle with a minimum and maximum. And in this case, I'm just setting the maximum. The minimum will implicitly be 0, 0. And the maximum is event.size, where event is the frame event that we received. So event.size tells us how big is the entire application window. And we're just going to use all of it. And then over here, I'm setting the corner radius via some math and multiple applications of the minimum function so that no matter what the window size actually is, we never set the corner radius to be more than half of it, because that looks really bad when, it just doesn't look good when it tries to round itself more than half of the window. It starts getting pointy on the edges. But an interesting thing happens when we apply clip operations, because we apply them with a function called push. Clipping is actually a stack. So we apply, hey, we want to work with this area, and then until we pop that operation off of the clip stack, we are limited to working within that space. And this is pretty useful. So when we push this, we actually get a return value. We get this area, this clip.stack value back that I'm called area here. And that area we'll later need to call pop on in order to allow drawing outside of the boundaries of this clip. Then we're going to set a color. This is identical to how we set the background color of the window earlier. We're going to say, hey, make it blue. And then we're going to actually paint, because setting the color does not change anything visible. So that creates a blue rounded rectangle that you can see. To make it act like a button, we have to tell Gyu a little bit more, right? So we have a pointer package that provides pointer input operations. And here we're saying, hey, the current clipping area, because everything works relative to the current clipping area. The current clipping area accepts pointer input. That's what pointer.inputOp means. And then, as I mentioned earlier, these tags, just some unique value for this widget. So we're going to use the address of the stateful part of this widget. It's whatever, as long as it's unique for the widget. And then what kind of pointer interaction do we actually want? Because there's a number, like scrolling, not relevant for a button. We don't care, right? So here we're just saying, hey, if you push, if you touch, and if you release, we want to know that. We're also going to say, hey, this clipping area semantically is a button. That tells Gyu to make screen readers and other accessibility software aware that this clipping area on the screen represents a button. I'm going to briefly skip over this section. We will return to it because this is the animation. It's slightly more sophisticated than the text. To display text, we're going to use exactly the same process of creating a clip, setting a paint color, and painting it. It's just that in order to get a clip for text, we have to shape the text. Text shaping is a deep subject, shall we say. It involves a lot of things. There's a lot of, choosing fonts, handling international text in different languages and mixtures of different languages. It's beyond the scope of today. But this function here is, I've written a sort of minimal API surface shaper wrapper for this example that lets you do very simple text shaping with a easy API. So we provide a string. We provide this metric type that allows us to scale how big things are based on the actual pixel density of the display. That comes to us from the frame event. And we provide how big the space that we're trying to render the text into is. And this shaper is going to give us back two things. It gives us back a clip.path, which is a outline described in terms of Bezier curves and lines and arcs of the text glyphs. And it gives us back an offset at which to position the origin of that text so that it's centered. So this particular shape function is kind of special cased for what we're doing here, which is drawing a button with centered text. The real text shaper API is more complex, but has a lot more flexibility. So to draw something at an offset, there's an operation, offset, surprise. And you can push an offset. So offsets and other coordinate space transformations have their own stack, like clipping. So we can push this operation, and it's going to shift the 0, 0 of subsequent drawing operations, or subsequent all operations, by whatever the offset is. We support general purpose two-dimensional affine transformations, not just offsetting. You can rotate and shear and scale things, and it works in sort of the same way as the offset, but we don't need any of that right now. Then we want to clip our text, right? So we got a path back from the shaper, but there's actually two things we can do with a path. We can use it as an outline so that we clip the space inside of the area defined by the path, or sometimes you actually want to draw like a line. right? A line that follows the path, but you're not trying to like fill in the interior. And that's called a stroked path. And so we have options when it comes to how we use a path. And in this case, we're just trying to display text. So we want to fill in the inside of the path. So we create a clip.outline. If we wanted to instead draw a line around the perimeter of the text, we would use a clip.stroke. And again, we push this clipping area onto the clip stack. So now, once this is on the stack, we can no longer make visual changes outside of the boundary of these text glyphs represented by the path. So then we're going to set a color. We're going to paint. And while this clip is on the clip stack, every operation is relative to the current clip. We're going to semantically say, hey, this clip represents text, and the text is label. So this is how we tell a screen reader, hey, this is what's on screen right here. It's how accessibility software knows. But now we're done with the text. So we pop that clipping area. And then we no longer need that shifted origin in the coordinate space. We're going to pop the transform. And then we're done with our button in its entirety. So we pop the outer rounded rectangle. So that's everything except the animation. So the thing to keep in mind when you're developing animation in Vue is that everything you draw one frame at a time. The only information you actually need in order to animate anything is how long should the animation last and when did it start. Everything else you can compute as a function of time every frame. Each frame tells you when it occurred. There's a field called now, and it's the logical time of the frame. If you literally look up what time, using like time.now or something in the middle of your layout code, depending on how long layout takes, you can end up with like subtly different values depending on where you call it. And you can get some weird like animation skew. So the frame just tells you, hey, logically, it is this time. Simplifies things. So here we're going to define that the click animation takes 1,000 milliseconds. And we can play with this value if we want it to be faster or slower. And then this if statement says, hey, event.now.sub, so the logical time of the frame, subtract the time that the last click occurred, right? That's going to be assigned to elapsed. And then if elapsed is less than our animation duration, we're going to draw some animation code. And otherwise, we just don't execute this if block. So we never insert these operations into the operation list, so nothing is drawn, right? So we use control flow to guide whether or not things end up in the operation list, which guides what shows up on screen. So if we're going to draw something, we need to figure out like how far through the animation are we? So this is a way of normalizing. We take the elapsed time divided by the total animation time. We're going to get a value between 0 and 1 for how far through the animation we are. Now, if we wanted this to feel a certain way, if we wanted to feel like springy or I guess like many animations do not follow a linear curve, but almost all of the fancy like easing functions accept a normalized value and give you back a different normalized value. And so right here is where you would make that modification. If you wanted this to be like a cubic in-out, you would take progress and you would apply whatever easing you want to get some other value between 0 and 1. And then you move on, and everything else is just defined in terms of progress, in terms of how far we are through our animation. So the way that we animate a click is we draw a circle at the location of the click, and the longer it's been since the click occurred, the larger the circle is, and the less opaque it is. So it starts out opaque and then fades so that you can see the blue through it as it grows. So we compute the radius as a function of how far we are through the animation, and also the size of the button, right? The size of the area we're working with. And similarly, we define the opacity in terms of the inverse of progress, 1 minus progress, right? How far do we have to go? Times the maximum opacity value. Since we're working in RGBA, everything's represented in 1 byte. So the alpha channel has 256 values. 255 is the highest representable alpha. So the alpha should go down the longer we are through our animation. So we construct a special white with the opacity set to whatever value we need. Making a circle is just a simple case of an ellipse. So we use the ellipse construct and do a simple we define the ellipse in terms of a rectangle containing the ellipse because it's unambiguous. And we take the origin point where we want to draw our circle, and then we just subtract on each axis to get the minimum point, subtract the radius of the circle to get the minimum coordinate, and we add the radius to both axes to get the maximum coordinate. So we end up with a square box with a side length equal to 2 times the radius around our point. And Guillaume will draw an ellipse that passes through that, which will be a perfect circle. We set our paint color to our translucent white. We paint it. And because we have pushed this clipping area that is an ellipse, the paint only fills that circle. And if the ellipse grows larger than the outer rounded rectangle, because the rounded rectangle's clip is still pushed on the stack, we're limited to the intersection of everything in the clip stack. So nothing bleeds out of our button into the surrounding UI. Then we're done with the circle. So we pop that clipping area. And here's a fun operation. Invalidate says, hey, Guillaume, at whatever the system frame rate is, make another frame. It's a way of requesting a animation to be smooth, right? We can go ahead and schedule, hey, next time the system is ready to draw a frame, go ahead and send us another frame event. So while you're doing an animation, you insert invalidate ops to ensure that you smoothly draw new frames. Because in GUI programming, unlike, say, video games, we actually don't want to draw frames all the time. Drawing a frame is much more expensive than doing nothing. So we want to do nothing when we can. That's it. That's all of the code to draw this button. And it's pretty easy if you want to get in here and mess with the ellipse, mess with the radius, mess with the duration, add easing functions. You can change the behavior of this button very simply. So I'd like to take this moment to pause and ask if you have any questions. We have the Ubuntu cube here. Feedback of any kind would be somewhat helpful.
One, two, yeah. Perhaps for some people who also didn't attend your previous talk, maybe you could show the animation of what you mean by the scale and how the components are growing, so people can have a better idea of what do you mean when like minimum area, maximum area.
I see. Yeah. So this particular example doesn't work with the layout system that I discussed in the previous talk. What we're doing is we're using the entire space available within the frame event. So the frame event comes to us. We can like jump to the definition of a frame event, right? So a frame event tells us a number of things. It tells us what's the current frame's time. It tells us this metric value, which allows you to convert logical units like display independent pixels into physical pixels on the current display. You know, like iPhones have silly high DPI, so you need to, you know, double or triple the number of pixels you use to get the same perceived size. You get a size which is like the pixel size of the screen. You get insets, which represents sort of parts of the screen that you can't use because the OS is using them. So like on Android, there are parts of the screen where the status bar is like covering your frame buffer. And if you use like the buttons, like the on-screen Android buttons, they can cover part of your frame buffer too. And you're like legally allowed to draw there in the Android drawing model. It's just, you have to know that, you know, if you put text there or something, it's going to be indecipherable. So the insets tell you that. So that's how we know how big the screen is. And we're not working with a minimum or a maximum size right now. But I can talk about that because it's going to matter for what we're doing next. So I'm just going to steal my own slide as a way of getting that visual quickly. Well, I thought quickly, but you know, Google Slides is going to make it less efficient than I dreamed. All right, here we go. So the higher level layout API that GUI provides, which we're going to be using for the next thing we do, is inspired by Flutter's layout API, but works in terms of minimum and maximum constraints. So to draw anything anywhere within the layout system, you tell it, hey, here is the least amount of size that you must occupy on the screen, and here's the most space that you're allowed to occupy. And the thing has to be somewhere between those two sizes. So this thing on the right here is a visualization of me messing with the constraints for two different text widgets. And text is kind of why the system has to exist this way, because text varies in size a lot more than, say, a button or like an icon or something like that. Text has to line wrap at whatever your maximum size is, but it also, if you want to like center text or something, how much space it centers itself within is governed by the minimum amount of space it's allowed to use, right? You say, hey, I want this text to be centered within the entire window, right? So the minimum X constraint for this text is the width of an entire window, and then the text will center itself within that space. So as the red rectangle that I'm dragging around right here is the maximum constraint, and the purple is the minimum. So you can see whenever the purple exceeds the green being the current size of the widget, the green is forced to grow to match, right? Because the minimum amount of space that the green can use is increasing on whichever axis. So here, you know, I drag the purple sideways, and the word hello has to use more space, even though it doesn't have anything to draw there. It's required to. But when I squish the red, the maximum sideways, the letters are forced to wrap to the next line because it's not allowed to use that much space anymore. So in GUI's layout API, we recompute the size and position of everything every frame. It's not actually very expensive. It's like addition and subtraction. Pretty highly optimized operations on a CPU, no multiplication required. And what that gives us is the ability to respond really easily to resizing, right? When your window resizes, or when some piece of content within your window resizes, we don't have to execute some kind of callback system. Some widget got new text in it, and so it's bigger now. And now it needs to let its container know, hey, I'm bigger. And then the container needs to figure out how to allocate space and potentially work up its widget subtree, which might cascade to other trees. It's very easy in a system like that to introduce some kind of bug where a widget doesn't resize properly. And this is kind of why responsive design is hard, right? Like why it's difficult to make applications that smoothly resize across a variety of possible, window sizes or screen sizes. But in Vue, because we just redo the math every frame, we just don't have that problem. You can't get stuck at the wrong size because we figure out the right size every frame. Yeah. So, does anyone else have questions about this button before I move on to something more sophisticated? Can someone toss him the cube?
Hey.
Hi.
So I guess I don't have button specific questions, but it's button adjacent.
Okay.
I'm more interested in the back end of this thing.
Okay.
So let's take Linux as an example. Is this all being rendered with OpenGL or OpenGL? Are you talking X or Wayland?
So
what's supported there?
So Vue supports the native accelerated graphics platform for every operating system we target. So on Linux, by default, we use OpenGL. We have a Vulkan backend as well. And you can like switch between them as necessary, or if the OpenGL one fails to initialize, we'll try Vulkan. On Windows, we use DirectX. On macOS, we use Metal. So we're using whatever the system preferred graphics acceleration library is. But on Linux, we also speak both X and Wayland. Depending on what your environment is, we'll prefer Wayland. If you're Wayland, we'll do Wayland. But if you're not Wayland, we will run X. We try to use the most efficient technology available on your platform.
And are you basing that off a third-party library, or are you writing the protocol clients yourself and everything and hooking that up?
So, we use EGL to like acquire GL contexts on platforms where that's relevant, right? Mm-hmm. But the stuff above that is ours. We're doing the Wayland protocol stuff ourselves. We're doing the GL management ourselves, Vulkan, etc.
Cool. Thanks.
Other question, or should I move on?
Hi. Is the button text rendered itself in the button context, or it's rendered inside of the frame?
Can you clarify what you mean by rendered?
Well, I just play it around and I see my text is inside at the center of the window, but the button size resizes and the text is not like joined together with the button. It does not resize like that. Do you understand?
Let me attempt to replicate what you just said, and then I'll see if I can answer you intelligently. Okay. So you resize the window?
I divided the button rectangle by 2, and the text was outside of the button, meaning in the code by itself.
Okay. I would really love to help, but I don't think I understand what happened.
I think I cannot clearly take my thought and define.
Okay. Well, we can chat after if you're still curious. Sure. Okay. So that's a button. That's an entirely hand-rolled example, and the purpose of that is to illustrate that the low-level API exists. You're not expected to use that API for everything because it's like super verbose and super granular. If you're building your own UI toolkit and you want to use us as like a backend or something, that maybe that's what you would do. But the bulk of people using Vue for things use higher level abstractions. So I have another application, and this is the one that requires SQLite. But this is a to-do list application, sort of a generic catch-all, let's try out a GUI type of thing, where we have a list of things that we want to do, and they're editable, right? So, and you can see this indicator that it's saving that edit. And we can supply some details, and we can mark it as complete or incomplete. And we can define a new task. So if you look at this interface, given what you know about Vue's operation list, you can see operations, right? You can see that we have rectangles that are clipped and filled with color. We have rounded rectangles that are clipped and filled with color. We have an icon for this sort of outline here, and this checkbox, and that's described as a path that is filled with color. We have this text, and this text is, again, converted to a path and filled with color to display it. So this is what a more realistic Vue application looks like. And what I wanted to do was give you a chance to play with some of the layout primitives. So let's look inside of this application. So this app is using Vue's highest API level. So we have a similar main function that's going to launch our application. And just like last time, in order to be cross-platform, we have to sacrifice the main Go routine on the altar of macOS and call app.main, and then do everything that we want to do in a different Go routine. We do some setup work. This stuff is not especially important for understanding the high level of what's going on, but we set some things up. We create a new application window. We choose a place to store a SQLite database on disk so that our changes are persistent. We build some backend logic. And my goal here today is not to try to convince you that writing GUIs is a trivial thing, because a GUI is actually the tip of an iceberg, right? It's the part of an application that you see, but it's usually not the biggest part of an application. You have to write a ton of backend code to implement whatever the logic of the thing that you're doing is. That's usually unrelated from the GUI. And so I have a backend thing here that does database crap to implement a to-do list, right? And that's something that you'd need to build for your application, no matter what domain it's in. And hopefully we don't have to worry about the backend stuff too much, because the thing that we want to talk about today is the UI. But I didn't want to build a UI that only did stuff in memory within the address, like within the local variables of the UI, because that's kind of useless. If you don't have the ability, if you don't see any patterns for how to persist state outside of the memory of your user interface, you can't actually build many useful things. So that's why there is a backend here. This application is like slightly realistic in terms of it can make persistent changes to its environment. So we do some logic so that the backend can like shut itself down. And then we build a UI type using our backend and our newly instantiated window, and we ask that UI to run. So this is sort of just an abstraction over the event loop The UI has a number of fields. It hangs on to the back end. It has this thing called a stream controller, which is going to allow us to do reactive data loads from the database. So whenever data changes and we're interested in it at the UI, we can get the data pushed to us in the UI. It has the window from view. It has a page, and this page is going to define the actual layout for the interface that we see. And then I've instrumented this application a little bit so that we can take a look at some performance stuff. And so these two fields are about tracing, which is a cool thing that the Go runtime makes really easy. So new UI doesn't do anything especially interesting. It just initializes the structure. There's this hotkeys function, which just installs the event processing and input operation to subscribe to Control N and F1. The bulk of this logic is activating tracing and writing it to a file. So the run function on the UI executes the UI's event loop, and it's kind of the same event loop that you've already seen. So we're going to execute over the Windows events, and for each event, we're going to look at what's the concrete type. Is it a destroy event? The window's closing. Is it a config event? That means like the Wayland compositor or the Windows system has changed something about our application's configuration, like maybe it stopped providing window decorations or something. And then there's the frame event. I've wrapped the frame event in a trace region, which lets us easily measure how long it takes and get some statistics about that. But here's where things diverge. So we still have an operation list like last time, and it's just a local variable in this function up here. But we're going to wrap it in a context. So a layout context is the primitive that provides constraints, the minimum and maximum constraints that I was talking about earlier. So initializing this layout context is going to automatically empty the operation list. So we don't have to like remember, hey, after I do the frame, I'm going to reset the operation. Like that's part of this. And then we give it the frame event. And when we give it the frame event, it automatically copies things like, hey, the maximum size of the window needs to be the maximum default constraint. And every widget might need to know about how to convert between logical and physical screen pixels. So we're going to copy the screen metrics into the layout context. So the layout context is sort of a wrapper around your operation list that adds constraints and a couple of other small quality of life things. I need to take a drink. Hang on. Okay. So as you saw earlier, we have a hotkeys function, and all that does is install some key logic. We're not going to go into a lot of detail on that. And then we do the layout pass for our page. By convention in geocode, we call the layout context GTX, the graphics context. You can call it whatever you want, right? But most of the code out there calls it GTX. And the reason for that, I suppose, is that Go has a context type that's used for lots of other things, and it's always called CTX, which so it's like taken. And if we called it CTX, it would be confusing to code bases that have both those contexts, which are about managing the life cycle of asynchronous resources, and a graphics context. But this layout function just inserts a bunch of stuff into the operation list using the constraint system. And we'll look at how the constraint system flows. And then like before, we have the part where we take the frame event and we hand it, here's an operation list describing our frame, you go render. And so I've wrapped this in a separate trace region so that we can actually look at how long does it take to do the layout? How long does it take to do render? How long does the frame, entire life cycle take? And then this last part is part of the reactive data load system. It's some bookkeeping that we do so that parts of your UI that are trying to reactively load data but are not visible, are not actually being laid out, can shut down their resources until they're visible again. It's just a resource conservation thing. So let's briefly talk about the page. So page is defined in a different file. And it uses the material design package that GUI provides. Logically, what the material design package does is it creates a type called a theme, and then a whole bunch of styling options that use that theme to choose fonts and colors and a whole bunch of little presentation details about how to display widgets. Then we have some state related to loading to-do tasks from the database and displaying them, and some state for a form, the form at the top that lets you create new tasks. So to make a theme, you just say new theme, and this is something that you do one time, not like every frame. Your theme actually holds a lot of things, including the text shaper. And the theme provides a higher level API for accessing things like the text shaper. We're going to set the default font face to something hopefully kind of decent, some sans serif face that is not random. And then we're going to configure a handful of fields that are widgets. So we're going to set like the text editors that you use to create tasks. We're going to say, hey, we want these to be single line only editors. You know, if you hit enter, it should not create a new line. But also if you hit enter, we want it to like logically act as a submission. We want to get a special event letting us know that the user tried to submit the contents of the editor so that we can go ahead and try and create a task when they do that. We don't want to force you to click the button. And we're going to do that for both of those text editors. This part right here is us saying, hey, backend, please, would you give us a dynamic stream of all existing tasks? And every time there's a new one, please ship us an updated list of tasks. So page has an update function. It's like the logical structure of what we're looking at is similar to the button we were looking at before, in that basically every piece of UI, it needs an opportunity to react to change from the user. It needs to process any user input events, and in our case, also process any asynchronous events coming from these data streams. So we don't want to create multiple copies of the same thing when the user is like composing a new task. And the best way to prevent that while also being able to handle things like failure is to disable the UI while we're trying to create a task until we succeed. And so what this logic is here to do is to wait until any pending task creation resolves and let us know, like if it failed, we're just going to let the user know that it failed. If it succeeded and there is a new task, we're just going to clear the form so that you can use it again. And then we're going to run the event processing for our text editors. So, if they did submit, we're going to track that and update the relevant fields. If you click the create task button, we want to also try and create a task. And so this is the logic that executes that and launches a asynchronous, hey, let's actually make a task with this data. And we can stream the result of that making task operation, which is what you saw us do at the beginning of the function. And then to lay out our interface, this is where we actually start working with that graphics context in earnest. The very first thing we do is call update from our layout function. So we want to make sure that our state is correct for right now before we display any of it. And then we start using layout primitives to draw our UI. So layout.flex is the single most versatile of these primitives. It resembles a CSS flexbox, but it provides a facility to lay out a sequence of widgets in either a vertical or a horizontal line. But you have two choices for what constraint policy you want to apply to any given widget. You can make a widget rigid, or you can make a widget flexed. If you make it rigid, you're essentially saying, hey, when you lay this widget out, give it all the space available in its maximum constraint. Allow it to use as much space as it wants. But don't force it to. And whatever space is left when the widget is done laying itself out becomes available to other rigid children. We lay them out sequentially in the order you provide them. And then after all the rigid children are done, if there's any space left and you have flexed children, the space is divided among the flexed ones. And so this gives you a lot of ways to allocate space between widgets. You know, you frequently have a fixed size content at the beginning or end of a sequence of widgets in the UI. And so you frequently make those things rigid. And then you might have content or images or any number of things that should fill the entire space between them, and you can make those flexed. Additionally, if you don't use any flexed children at all, there's a field called spacing that lets you control the policy for how leftover space is distributed if it wasn't all used by the rigid children. So you can do things like, hey, put space divide the space evenly between all of the children, or you can put all the space at the beginning, all the space at the end. There's a lot of different policies that let you implement quite a few things. And so here, what we're doing is creating a vertical flex. So we're laying out a sequence of vertical things. If we need to show a header, which is something that we have to worry about for things like Wayland, where you're not guaranteed to get window decorations from the compositor, so you might have to draw them yourself. We handle that. And if we don't need to show the header, we just return empty dimensions. We say, hey, this child occupies no space. And what's cool about this is that we actually didn't insert anything into the operation list if we take this branch here. You know, we were given a GTX, which contains an operation list, and we checked, hey, do we need to show something? And we don't. So we just don't do anything to the operation list. We say we use 0 space. And this means that during render, this was free. During render, looking at this branch costs nothing. But if we take the branch, then we lay out a header into the operation list, and we return how much space it used, and that's subtracted from the space available for the others. So in our case, the next child is a rigid form, right? That form that's at the top of the UI. And then a flexed, so it gets all the remaining space, list that we can use to scroll through all the items. And so I'm going to run the app again so that with that additional context, you can look at this. So here is actually the Wayland window decorations provided by GUI. So we're actually skipping drawing the header in this interface because we're on Wayland and there's already a title bar. It looks very silly if you draw both of them because it's like double thick. One of them has, window controls and one of them doesn't. It's goofy. Then you have our rigid create task form. There's that button. These are the 2 text editors that you can submit. And then here is our flexed list full of items. Sorry, I don't usually use GNOME, and I keep trying to use the wrong keyboard shortcuts. So I want to kind of focus in on the individual items that we're laying out to represent a task. So we have a simple data type defined by our backend called a task, right? And it's just a unique ID, like a database ID integer, and a name and some details, and is the task done or not? And we need to manage this task from the UI. We want to enable the user to manipulate it. And so we need a text editor that lets you manipulate the name, and a text editor that lets you manipulate any like additional details you want to track, and a thing you can click to toggle whether or not you consider it done. And so that's what these three fields are. So the widget package in GUI provides state types representing the like essential state of widgets that do not have an opinionated way of displaying them, right? So this is like, hey, it's tracking the state buffer for these editors. What are the concrete text that's inside of the editor, but other than knowing how big the space that it's drawing the text within is, this doesn't know anything about this sort of display. It doesn't know what color the text is. None of that matters for the essential logic of being a text editor. All of that's sort of a display time thing. And that's what package material is going to bring us down here. This style type, task style, wraps a task state in logic about how to display it. So during a frame, we make a task style and we give it a theme and we give it the state that it's trying to display. And then it wraps each of these unopinionated, editors in a material editor. And the material editor is defining the color of the text and positioning, and the icon button wraps our clickable state in all this logic for a button with animation and displaying an icon. That little like saving indicator is this material.loader type. And if there's an error, we can display it with just a little text label. And so here we start configuring, for the various widgets that we're displaying, like visual fields about them. But the important thing to know is that this style thing, we make it for the purpose of inserting a bunch of stuff into the operation list, and then we throw it away. It's not expensive to build this thing and use it to construct our layout. This is basically a way of choosing colors and sizes and other aesthetic details. We could have written it many ways, but this is the strategy that GUI provides for you if you want it. Is you can take the style, you can take any state and wrap it in an ephemeral, hey, make some style based on this theme. And then it's easy to change the theme, and all of your widgets respond to that change because you're rebuilding the style every frame too. So just like our page, we want to, before we actually insert anything into the operation list, we want to update the state of our task, and that's going to handle, did the editor change something? Did a different application window edit this thing? So we need to update it. If we're done, if the task is marked done, we need to display a different icon, and we need to display a different sort of like accessibility text for that button. And then we're going to display the contents of our task that we're working on. So we're going to use a different layout primitive here called a stack. And a stack, and I admit this nomenclature can trip people up, is about overlaying things on top of each other, like literally stacked, not one thing above another. That's a flex, but stacking is overlapping. And so what we use this for is if we want to display something and then we want like a background underneath it, right? The icons, or so the items that we're displaying in our to-do list have a white rounded rectangle underneath them. And that's what we're doing here in this stack. Stacks can have two kinds of children. They can have an expanded child, and the expanded child is forced by the constraint system's minimum to be at least as large as all of the stacked children. So the other child that we lay out is like all the text editors and everything, all the UI inside of our rounded rectangle. And GUI does all the work to lay this out and take its resulting size and then force the expanded child via the constraint system to be the right size underneath it. And so within our stacked child, we're going to make a horizontal flex, lay out a sequence of things in a line. And we'll align all of them together by their vertical center point, because flexes can also control alignment, which is really handy. We will lay out a button, the button that we're using to toggle whether or not the task is marked done. And we'll lay out all of our editors. So this is a helper function. And it's helpful in GUI in general to break your layout down into smaller units that are easier to digest. As you have seen, the current layout API has a fair amount of nesting. And so you don't want to slowly drift to the 400th column of text. But it's not so bad when you can just use helpers. So this helper function just is responsible for laying out the editors and the loading indicator. We're going to inset it. So this is another layout primitive that does a very simple thing. It just carves out a certain amount of space from the maximum constraints. So it shrinks the constraints and centers whatever it wraps to add some margin or some padding. But it's all handled at the sort of constraint level. So you just say, hey, I want to inset this thing, and then the widget that you lay out inside of it automatically has its constraints adjusted to reflect that insetting. And then sometimes we actually, so this is what manipulating the constraints directly looks like. So we say gtx.constraints, and then it has two min and max points with an x and a y coordinate. And so here we're saying we want these text editors to be full width. We want to make sure that even if you click, far to the right of where the text actually ends, that the editor is still there to receive your click so that it gets focus. Because otherwise, if your text is like one word long, you have to click inside of that text. Kind of sucks. So this is how we say, hey, make everything here use all of the horizontal space. And then we're going to use another flex to stack our editors on top of each other. And it's going to have a number of children, right? It has one gigantic rigid child at the beginning, and then a whole bunch of much simpler ones. These two are just spacers. Their whole point is to spread out the other editors and widgets around them. And this top one is just laying out the name editor and then the sort of loading activity indicator. So the name editor is flexed. It gets all of the space that's not used by the rigid children. and the loader is rigid. So it just gets some amount of space that it gets to choose. And since they're laid out in order, it's like the name visually is first, and then the rigid at the end. And so we're going to constrain that loader to be exactly like a 20 by 20 logical pixel space. And if we're not updating, then we're not going to display it at all. We're just going to return the space that we would have occupied. So that's what the logic that does all of this looks like. Now you might have noticed, oh Lord, the latency on this thing is just terrible, right? I click something and then there's this loading indicator and it doesn't feel good. And that's because that's entirely fake. I put in some sleeps in the code so that operations took time, because otherwise you wouldn't have been able to see any of that. So if you use the latency flag, forgive the typo. It's essentially instant. And we can actually open multiple windows. That's what Control-N does. And you can see that both windows receive the application state update instantly because they're both reactively streaming the state from the database. But we can also do cool stuff like press F1, make a new task, and another. And then we can edit this one. And, you know, the edit is being saved as we type it, and we can mark it as done, and you can see it change in both windows. And then we can press F1 again, which will end our tracing session. And we get to look at it in GoTraceUI, which if you install GoTraceUI, which the instructions are in the README of my repo, then it'll open it for you. And you can come in here and you can see here's our event loop function. And we can do things in here like open a flame graph that describes what our event loop was doing. And most of what our event loop was doing was sleeping idly. But this is the very small percentage of that time that we spent actually doing layout and rendering. We can also come in here. You saw that I did those trace regions, right? So that's what these pink things here represent. So we can look at a frame, select the region. It's kind of awkward using the super blown up interface like this, but here's the histogram for how long it took to do frames in general. So the longest frame observed during the trace was like 11 milliseconds, but they cluster sort of around 4, 5, somewhere in there. So we're like well ahead of the 16 millisecond deadline that you get for a 60 hertz display. It's really unfortunate that I got scrolled to Kingdom Come because I really wanted to show you. All right, so the layout pass, right? If we select that region and look at its histogram, layout by and large takes less than a millisecond. A very, very small amount of time, even though we're redoing all of the layout positioning, we're choosing the colors, we're all of that stuff. It's cheap. And rendering is not much worse. So this is all the GPU work, and it's like the sort of median rendering is around 3 milliseconds. The worst one is somewhere up near 7.3. But that one is probably where we had to upload all of the paths representing the text to the GPU the first time, because you have to get them into GPU memory somehow. And once they're there, if you keep using them, they stay there and you never have to do it again. So I wanted to display this so that you got sort of a sense of what performance is like. This is a laptop that is, I have a 7th generation Intel processor. So it's 7 years out of date, something like that. Probably much weaker than all of your computers. This is the global flame graph for processor utilization during the execution. And so the bulk of time that we did spend on the CPU, obviously this doesn't account for time that we spent doing nothing, was spent actually rendering, right? So this GPU.frame, this is interacting with OpenGL to do the render. And over here, this much smaller section is various layouts and then Go runtime things. And actually, I guess the database is somewhere over here too. So I think this subregion is the UI. So we spent a total of half a second of CPU time doing UI work during the entire period I traced. That's the layout part of UI work. So yeah, that's a somewhat realistic application that does a useful thing. The state is actually synchronized between windows and it will persist, open and close the application. So hopefully it's a decent reference for one way of achieving that sort of real state management. I put in that fake latency so that it would simulate, doing other things like API requests or other workloads that have real latency, because you have to design around that. But yeah, you can disable it with a flag, or you can remove that from the code entirely. I think I'd like to see if you have any questions now.
This is perhaps more of a Go question rather than this example, but if you would build this app, will it also add some extra optimizations? So we would expect this app to work even faster and be less resource hungry, right?
The go build command is a compile and run in one step. So there's no difference between the executable that I'm getting and the one that I would get if I did like a go build and then ran the executable. So I would not expect a difference in resource use there. Go doesn't have like multiple optimization levels in the compiler. The decisions that they have made as a toolchain are that every build should be by default the same like good level of optimized, but that should still be fast. Like the build process should still be fast to produce the optimized executable. Other question?
Do you have anybody who's using this for like a larger scale application? Oh, he does. All right.
I'm going to steal some slides from earlier. The Tailscale Android client is built in GUI. This is just sort of some cherry-picked examples. There's a casual social gaming platform called Plato that historically has used mobile apps to let you play like card games and other sort of fun network multiplayer games with friends. But they've recently launched a desktop application built with GUI. That's what you see there on the right. These two are more esoteric, but kind of fun. You've seen one of them today. Go Trace UI is built with GUI, so it can trace itself and all sorts of fun things because it's a UI in Go that visualizes Go execution traces. The one in the back is sort of a fun project called Ubuntu. It's from the 4K demo scene. So people who try and pack the coolest audio visual experience they can into a 4 kilobyte executable. And Ubuntu in particular is a music synthesis tool that lets you build modular synthesized instruments and then compose tracks using those instruments. And then it uses this specialized compiler to build your instruments and music into a minimal assembly language implementation. So we're talking like a few hundred bytes to represent the music that you have composed. So this UI for doing that is built with GUI. The stuff that it's interfacing with is not all GUI and stuff, but the UI depicted here is the GUI interface you can use to control that. So those are my two-hand ready-made examples.
Cool.
I can skip. If I hit end, does it jump? Yeah. If you want to see this deck, and these are links to the various projects that I described, to that QR code will take you to this deck. Any other questions?
How much time is needed to go from this code to GitHub to real application that can run through Android or Ubuntu?
Sorry, give me just a second. The Java compiler is not super fast. And there is some Java involved because Android.
It means that if I modify this code and I make my own application, I do just like this, and I can.
You have to have some Android stuff installed. Like we don't re-implement the Java compiler and that sort of stuff within our own toolchain. But you can find instructions on the website for which things from the Android SDK you need to have available in order for this to work. But if you have sort of the build dependencies for these targets, it's very easy. And similarly, you can cross-compile applications pretty easily. Having SQLite in the mix in this particular example makes things harder because you have to have a C cross-compiler. But without SQLite, you can actually build apps for Windows from Linux trivially. So if we want to do that, we can say go OS equals Windows, go run, and then we're going to run in Wine. So what this is saying is, hey, go, please cross-compile this executable for Windows, and then when you get the resulting binary, execute it through Wine. And it's going to take a minute because this isn't in the compiler cache. And also I'm compiling for Android at the same time. So the CPU is pretty contended. And as I mentioned, it's kind of old, but we should get there soon. We can waste even more CPU time by trying to watch. Oh, look at that. HTOP is do I have to? Yeah, so you can see Go does a pretty good job of parallel computation. I believe the unit of compilation in Go is individual functions, not files or something, and they're fanned out across the CPU cores, which is what makes builds very quick, except when you kind of defeat all caching infrastructure by compiling for a different operating system on a machine that you don't do that on enough for it to be in cache. I was hoping that one of these things would finish, but yeah, obviously if you need to go, thank you so much for coming. I appreciate your time and attention. Poor little laptop is gonna melt. I could cook an egg on it. but I'm going to give up on Android because I think that that one's slower, and hopefully we can get the Windows one. Any other questions while this builds?
Do you have hooks for device-specific sensor data or camera, GPS, gyro, that thing?
Core Geo does not provide modules right now for interfacing with device hardware sensors such as the accelerometer or the GPS, but there's no fundamental obstacle there. You just have to kind of write a little bit of interface code to talk to the device's API. Yeah, and I mean we have some examples of that in. So Core Geo tries to provide only things that like every application will need. And then there's another repository, GeoX, that has some extensions to that. And like one of them is desktop and mobile notifications, right? And that's an example of a place where we had to interface with the native API for that for each target platform kind of individually. So like on macOS, we had to write a little bit of Objective-C. On Android, we had to write a little bit of Java. But it's like not that hard to surface those capabilities. And you know, if someone does the work, usually that work can join, you know, one of the official community repositories so that it's easy to share. Oh yeah, so we have our button. Now it's interesting because there is no text. I don't to hand have a explanation for this. Yeah. My guess is that there's some subtle DirectX emulation thing at play here, but I don't know. It's probably fixable, and I don't think it's happened to me before. So I don't know.
There is on line 5. Setting line 5 is not
Oh, it's a fix me too. Yeah. So I think we've tickled a DirectX bug in Wine. Yeah. Well, that's all. I'm happy to talk more if you run into me or want to hang out. But thank you so much. I appreciate your time.